All right, hello everyone. This is worksheet 13.1, and in this worksheet I'm going to show you a derivation of the Boltzmann distribution using a different method than is presented in the book. The book shows, I guess, a more common way of deriving the Boltzmann distribution that involves using fairly advanced calculus concepts like Lagrange multipliers. And I would highly encourage you to see if you can work through that derivation in the book in addition to this one, because approaching this problem from two different directions is just, I think, is a good idea. But I'm going to present the Boltzmann distribution using something different and something maybe a little bit unexpected. I'm actually going to use the atmosphere to demonstrate the Boltzmann distribution. Okay, so in this derivation, let us consider a column of air. And in fact, maybe a better way to think about it is a column of gas, because air is, of course, a mixture, and we're just going to consider a column of all the same type of particle. So we probably may as well just say gas, though the Boltzmann distribution law does apply to the air. And all of the gas inside this column is the same temperature. So therefore, all of the gas particles inside there will have the same average kinetic energy. All right, and that's what I've got depicted over here in this little figure. I've got a landscape down here, and then I've got a very tall column that goes from the area of the atmosphere that's thick and dense at sea level, and then goes up and extends up into space where I've drawn these stars. All right, and this column is full of gas particles. Obviously, it's going to be fairly sparse up there at the top, but then it's going to get denser and denser as we go further and further and further down until we get down here at the bottom where it's quite a bit denser. That's at least what the Boltzmann distribution tells us. All right, so let's start by considering the force that a particular particle might feel inside this column. It's going to be equal to the mass of the particle times the gravitational constant. Hopefully you remember that from physics. So here is the mass of particle, and this is the gravitational constant. And that's going to be in units of acceleration, and by the way, this is specific to Earth. If we were on a different planet, then it would have a different gravitational constant. Okay, now following the definition of our force for the particle, let's say that we've got a potential energy for the particle. That now is going to be equal to the mass times the gravitational constant times the height that the particle is above the surface of the Earth. So we can say this is the height of the particle. All right. So going from there, let's calculate the amount of pressure that a single particle is going to exert, say if it was on the ground. Or it'll exert the same amount of pressure no matter where it is in relation to the ground, as long as the force remains constant. But we're going to say that this equals negative force particle, and I've added the negative sign there because it's in the downward direction, divided by the area of the column. Okay, so if you can imagine, I've got this circular column, and I've got a series of sort of like slices going down this column like that. And so I've zoomed up on one of these slices here, and the slice is going to have a very, very thin thickness, which we can just call DH, and it's also going to have an area A. All right, and so this area is the same as this area here, and as you can see, the slice is filled with particles that I've depicted with those little black dots inside there. And so therefore, the pressure exerted by a single particle is going to be negative mass of the particle times the gravitational constant divided by the area of my column. I'd like to point out that there's going to be a volume of that little slice, and that equals A times dH right? Because that's going to be the volume of a cylinder, because this is a very short, flat cylinder. And I could rearrange this equation algebraically to say that the area of the column is equal to the volume divided by dH. All right. Now, I'm going to represent the pressure caused by the entire slice. So the pressure of the slice, I'm going to represent with dP. All right, and it will become clear why I'm representing it that way, because I want to eventually find the pressure for a larger area of the column that's going to be made up of all the pressures of the individual slices all stacked up on top of each other, because the pressure that the column feels at a particular slice is due to the slice right above it and all the other slices right above it too. Okay, this pressure of the slice equals the number of particles at that particular height in the column, because it's going to be more sparse up high but more dense down low, multiplied times just what I have up above right there for the pressure caused by my particle, which is going to be negative mg over a. And I can just replace my expression for a there and say that this is equal to negative number of particles at that height times mg dH over the volume of the slice. Okay, I'd like to point out that the mass of the slice, which we can denote with the symbol ms at a particular height, because of course it's going to depend on the height up the column that the slice is at, is equal to the number of particles at that given height multiplied times the mass per particle. So remember, the NH is the number of particles in slice at height h, and little m is the mass of particle. Okay, let's continue. We know that P equals nRT divided by V, but remember that I can represent little n times r as big N times Kb, Boltzmann's constant, times T divided by V, like that. Okay. So if I've got, and that's the pressure of the column right above that location. So I could really say that this is a height-dependent pressure, and that pressure is going to depend on the slice right above that height, and then all of the slices right above it as well. So if I want to pull out the amount of pressure that's caused by a little slice somewhere in that column, then it's going to be equal to the pressure of some height plus the width of the slice minus the pressure of a given height. And this is sort of related to the definition of a derivative. So I'm going to write this as a derivative of the ideal gas law. I'm going to say that it's a tiny change in big N kBT over V. Now, which of those four things inside there are actually changing with height? Volume's not changing. We're assuming that the volume of each slice is equal. Temperature is not changing because I'm saying that everything all up and down the column are the same temperature. Kb is a constant, so therefore the only thing changing must be N. So some small change in N at a given height is equal to kBT over V, like so. And we've already found a definition of pressure right up here, so we can go ahead and just set those equal. I'm going to say that dN at a given height, kBT over V, is equal to the N at that height times M times G dH over V. All right, we can cancel a couple things out. We can cancel out the V's. And then what we want to do next is we want to divide both sides by 1 over NH, or I guess multiply both sides times 1 over NH. So I want to get the n's all on one side, and I want to get everything else on the other side. So I'm going to divide both sides by kBt. Okay, the kBt's cancel out on that side, the n's cancel out on this side, and what I'm left with is dn of h over n of h equals negative mg over kBt dh, like that. All right, this is a differential equation, and it's one of the more approachable types of differential equations that can just simply be solved by taking an integral of both sides. So we'll take an integral of both of those sides, and this side here is just equivalent to the integral of 1 over n dn, and if you recall, that just equals the log of n. And then this integral over here, all we end up doing is just getting a negative mgh over kBt. And of course, both of these sides are plus a constant, but we can just lump both of those constants into the same spot. So what we end up with is log n as a function of h equals negative mgh over kBt plus c. But now we need to get rid of that log, so we'll raise e to both sides of this equation, and the e and the log cancel out, and we're left with n as a function of h is equal to e to the negative mgh over kBt plus c. But this just equals e to the negative mgh over kBt times e to the c, because that's what follows with the rules of exponentials. If you've got an addition up in the exponential, you can turn it into a multiplication down at the level of the exponent. And we're just going to call this value here a, because it's going to be our normalization constant. And the final expression we get is that the number of particles at a given height is equal to a e to the negative mgh over kBt. But we already know that mgh is equal to the potential energy of a given particle. And so we can replace that inside there by saying that the number of particles at a given height is a times e to the negative energy of that particle, kBt. And that's it. That's our Boltzmann distribution. All right, well, that was the main point of this worksheet, but I guess I want to just point out a few more things. I'd like to point out that if you take the number of particles at some height 1, maybe it's higher or lower, I don't know, and then you divide by the number of particles at a different height, height 2, then you get a e to the negative energy, the potential energy at that height 1, and then divided by a e to the negative e2 kBt, like so. I'm just dividing the two Boltzmann distributions. The a's cancel out. And remember, if I divide two exponentials, then that means I can subtract what is inside the exponential. So this equals e to the negative e1 minus e2 divided by kBt. And we can directly relate this to probability. So the probability that a particle is at a given height 1 divided by the probability that it's at a given height 2 is also described by this distribution, and that's because ratios of counts is exactly the same as ratios of probabilities. And sometimes you'll see this expression where you've got the two energies subtracted, just delta E like that. It allows you to find the relative probabilities of two different energy levels. I'd also like to point out that the ideal gas law says that N equals PV over RT. So if I've got N1 divided by N2, then that just equals PV. If you've got, I guess, two systems of equal temperatures and equal volumes, The only difference might be the pressure. Like for instance, in an atmosphere, then this just becomes P1 over P2. So the Boltzmann distribution also describes differences in pressure at various altitudes. Okay, so if I want to explain the pressure at a given height above the atmosphere, if you assume that the atmosphere is all the same temperature, which is not a valid assumption, but maybe it's a good first approximation, then it's going to be equal to the pressure at sea level times e to the negative mgh divided by kbt, and this h here is the height above sea level. And using this expression, you can predict the atmospheric pressure at various altitudes. So that's kind of slick. All right, the last thing I'd like to point out is that the distribution is going to depend on this mass of the particle. So if I've got along this axis the height, say in kilometers above the Earth, maybe we go 20, 40, 60, 80, something like that. And then over here, we've got the pressure in atmospheres, then there's going to be 1.0. Imagine if you had an atmosphere of pure oxygen with a pressure of 1 atmosphere. Then my Boltzmann distribution might have a curve that looked something like this. So this would be O2. But if I, say, had an atmosphere of H2, then the low mass of H2 is going to change the shape of the distribution, and it's going to go down much more gradually because of its lower mass. And so for this reason, you're going to have different proportions in the mixture of air depending on what altitude you're at. So that's an interesting result of the Boltzmann distribution law.